ये लाइट ज़्यादा है, ज़्यादा है
बराबर है ना क्या लिया था वही तो लिया था लाइट्स कुछ प्रॉब्लम नहीं है यहाँ पर देखिए आपको कौन सा आगे इसको दिख रहा है लेकिन
A very good afternoon and welcome to this live session on this NPTEL course Advanced Transition Metal Organometallic Chemistry. I am the instructor of the course, Professor P. Prasenjit Ghosh of IIT Bombay, and I am accompanied by two TAs. Mr. A.P. Prakasham on my left, and next is Ms. Shreita Dey, and these are incidentally doctoral students in the organometallic chemistry, and today happens to be a very happy day for Mr. A.P. Prakashan, who has submitted his PhD dissertation. And today in this session, I welcome all of you to join with me in asking me questions, and I'd be happy to answer them. And as you can send me your queries through chat session windows, which I would be able to see and answer.
Yeah, it's all good. Yeah,
okay. And as queries, let me just answer some of the questions that I have received over the last few days. And to begin with, my first question says that, sir, can you please suggest me latest synthetic trends and applications regarding transition metal organometallic chemistry? Well, this is a very interesting area in a whole, and there cannot be a individual reaction or application that can be assigned to transition metal chemistry. And to illustrate my point, let me just reiterate the fact that there have been about 9 Nobel Prizes awarded in the last 70 years on type of reactions and their applications in the field of transition metal organometallic chemistry. And if you look at each of these areas, they span from something which is related to biomedical applications like organocellular compound for syphilis disease, or to some laboratory reactions, classical laboratory reagents like Grignard reagents, or in terms of applications to the area of polymerization like Ziegler-Natta polymerization, olefin metathesis, to even some very classical concept-based areas like sandwich complexes, which deals with metal ligand binding, or Woodward-Hoffman rule, to also very practical practical applications like asymmetric hydrogenations or palladium-mediated cross-coupling reactions. So what this sort of highlights is the fact that so what this is this field of organometallic chemistry has tremendous possibilities, and this has a huge breadth of reactions or huge scope of reactions that can be benefited or developed using with transition metal organometallic compounds. Now, to highlight some of the recent ones, as you have mentioned in your email, one can talk about biomedical applications of organometallic reagents, as well as material applications in photovoltaic or energy storage or some other or precursors to very important compounds in devices and etc. So in short, to sum up, that there are very many interesting reactions which can be attributed to the latest trends and applications in advanced transition metal organometallic chemistry. Now, you have a follow-up question which says that how to implement this in our college. This is a very interesting question indeed, in the sense that you want to adapt some of the latest discoveries of transition metal organometallic chemistry in your curricula in your college. And to answer this thing is that you need to have access to basic infrastructure, for example, like that of a good laboratory that can handle anaerobic conditions. And you need to have access to high vacuum lines. Then you need, because you would be required to use Schlenk techniques for carrying out organometallic synthesis. And you would also require solvent steels or solvent drying equipments or facilities whereby you can use pure dry solvents for your synthesis. Another must-have equipment that one needs to do organometallic synthesis is that of a glove box or dry box. Now, dry box is a small module, compartmentalized module containing inert atmosphere, which does not contain air, and it is usually filled with nitrogen or argon, and these environment argon, these are used to store compounds. So basically, these three things dry box, still, and high vacuum line is must to have to carry out any organometallic protocol in your laboratory or in your college. Apart from this basic thing, what you would require is spectrophotometers spectrometers like NMR, IR, UV, mass for characterization, elemental analyzer for characterization of organometallic compounds. So I think, briefly, I have spoken about the things that you would require to implement organometallic protocols in your laboratory, in your college. Now I move on to the third question, which says about strategy to crack GATE. I think this is an important question for many of the students, in particular, who are taking GATE. And the only thing that I can think of is that one needs to study hard. One needs to look at the syllabus, read the syllabus completely, and try to apply the principles. The principles that one absorbs in this textbook, and just prepare hard for the exam. I think there is nothing, no other strategy that can work other than just simple, plain, good old studying and covering the syllabus. Also, to look at some of the questions that had arrived in the previous years would give you clue as to what kind of questions are being asked, and how they have been used to test the knowledge of the students. So that solving last few years questions would also give you some confidence for going into this GATE examination for the following year. So now, apart from these three questions which had been on general topic, there is a technical question, which is the fourth question, and the question goes as: what is the d electron count of copper using neutral covalent method for electron counting? For nickel, it is 10. Then it is 11 for copper, but d orbital can accommodate only up to 10 electrons. Thank you. Okay. Now, to answer this question, one has to realize that we do all this d electron count by neutral method or the ionic method for transition metal complexes. Is bound to ligand. Now, in transition metal complexes, there are 3d, the inner d orbitals, then one s and 4s and 4p or 3p orbitals. So overall, there are about 9 orbitals which can take up 18 electrons, and these 18 electrons are filled from the electrons of the metal as well as from the electrons of the ligand collectively. And this total electron count that one counts, which involves the electron of the metal electrons and the ligand electrons, are called the valence electrons. Okay, so now coming back to the question, when you say that for copper, if there are 11 electrons, that would be for copper 0. Or 0. So for any copper 0 complex, these all 11 electrons would reside in the 5 of the d orbital as well as 1 of the s orbitals. And the remaining electrons would come for this copper 0 complex of the ligand from the ligands that are bound to copper 0, and they would occupy the s as well as the p orbitals. So in short, that all these electron counting is valid only for transition metal complexes which have d, s, and p orbitals. And they do not conflict the initial principle that any orbital can hold only 2 electrons. So that rule is valid for filling up any of these s, p, and d orbitals. I think I have been clear in answering the question that you have whether D can have 11 electron. Answer is no. D cannot have electron. D always can have at the most 10 electrons. And the remaining electron goes into the unfilled s or p orbitals that are available in that transition metal complex. So now we go to an interesting letter. I think there is a question number 6 that says, "Respected sir, this is Ayesha Begum. I'm a PhD student scholar at BA SCIST, Vendalur, Chennai. I'm taking this NPTEL course since I was interested and I'm gonna make use of this course as a credit transfer course. I just have a query, sir. Can you please help me? I missed the 08 assignment, unfortunately. Sir, will I lose marks for that? I will submit on time the following assignments 1 and 2. Thanking you. Well, I said, thing is, it's very nice of you to have asked this question for clearing doubts. It will not only clear your doubt, but also clear doubts of many and answer. And the answer to this is no, you will not lose any mark for not answering this 08 assignment, because that does not count in the overall assessment of the course. Sir, question number 6 is an interesting question again. Sir, how chemistry good for doing PhD? I think to answer this, that I have done a PhD in organometallic chemistry, and I have been able to succeed getting a job in one of the reputed institute of our country. So to me, that yes, this is a very important and nice, interesting area to do PhD. There are plenty of opportunities for good students. And the two TAs who are also the TA of the course are also doing their PhDs in organometallic chemistry. You know, and so I think organometallic chemistry has an edge over traditional inorganic or organic chemistry, because organometallic chemistry overlaps the area of inorganic and non-organic. Organic chemistry, and thus you will have a skill set for both the two disciplines, which will be inorganic and organic, and you will enjoy advantage over traditional inorganic or organic chemistry people. Also, lastly, I should mention that there is a student right now in my group who had actually joined this PhD program in organometallic chemistry. Again, after listening to this organometallic course in the previous semester that I offered it in the previous semester. So I think, yes, there are plenty of opportunities. It's a nice area to do PhD on. And if you are interested, you should also pursue your doctoral research in organometallic chemistry. So with this, we come to the next question, which says that my question is, there are any compound in which rectangular structures of cyclobutadiene possible? Yeah, you know, theoretically it is possible if the cyclopentadiene acts as a bridging ligand between two metal center, and but the one has to search the literature to try and see to get some well-defined examples of that kind of rectangular structures of cyclobutadiene ligand. So with these, we have one is the color of nickel chloride is green, while nickel DMG is rosy red. Even though it is in +2 oxygen state. What is the reason for this, sir? Okay, now see, you have like not. Let me answer this way. Not all metal center having the same oxidation state has the same color. It depends on how the metal center is interacting with its anionic ligands in covalent or ionic interactions, or what kind of ligand it is bound to. And also what kind of transition is possible from lower electronic levels to higher electronic levels. So overall color that we observe, there can be a overall color that we observe can arise from for simple metal-metal transitions like DD transitions, or sometimes even from metal ligand charge transfer or ligand to metal charge transfer transitions. So one has to really work out the detailed electronic structure of complex with the ligand involved in it. Electronic transitions they give rise to. To get some idea about the color, but it is not something which can be predicted directly based on the oxidation state. For example, manganese in KMnO4 is in +7 state with 0 d electrons, but it is intensely colored because of the charge transfer transitions. Furthermore, color also depends on the morphology of the substance. Sometimes, depending on the particular size and the type of the light it diffracts, the color of it would change or would vary. Of this, so to sum up, it is a combination of factors that gives rise to color, and that cannot be simply attributed to oxidation state or any particular kind of phenomenon. Okay, so the next question is a very strategic general question. It says, sir, is it necessary to cover all the topics for NET, or should we focus only on the areas that I have stronghold. Well, my answer to that is both. You should have stronghold, and also you should try to cover as much topic that you can possibly do, because sometimes there may be very difficult question in your stronghold area which you may not be able to answer, whereas there may be some very easy question in your not so stronghold area which you will be able to easily score. Sir, I think the best thing would be to just read as much, cover as much, and try to give your best at when you write your exam. So now we come to the another question which says, sir, I am 31-year-old and want to do PhD. What is the good out of full-time or part-time? Also, is there any funding from government at the age of 32? Now, this is that there is no age at which you cannot do PhD. It is solely driven by the passion for you to pursue the knowledge. So in that way, I would not say okay. 31 year is still okay time to do PhD if you really feel strongly about it, even though you are good 5 or 6 years late behind your contemporary friends who would have finished their PhD by 31. Now, between full-time and part-time PhD, I think PhD involves extensive engagement. And as a result, full-time PhD is better because you will be able to complete PhD in shorter period of time. Than part-time PhD, because that will take even a longer period of time to finish it. Now, as you are a bit late in starting, as you said, you're 31, so when it will take longer time to finish it, you will even get delayed further. So I think for you, maybe full-time probably is the quicker way to finish it. And regarding the funding opportunity available at the government level after the age of 32, that I think you check with the CSIR or TST websites. I'm not too aware of the rules and regulations. Regarding that, or you can join in some project stuff category where you can get funded through some project of your advisor. So with this, I think I have answered all of the questions that I have received today. And if you have still some more questions, all of you are welcome to send them. So we'll wait for some more time.
It's post. All done. When will be the next session? Did you say that? When will the next session? Next
Tuesday.
Just for that information next week.
Okay. So if there is no further question, I will conclude today's session.
More post session.
He's asking to wait.
A few minutes to post.
And next week we'll schedule this session to be on Tuesday. Tuesday at 3 to 4 p.m. For joining me in this live session. I look forward to meeting you on the next session, which should be next Tuesday at 3 to 4 p.m. Thank you.